Hello. So my talk is titled Lessons Learned Building a Cloud-Native Geospatial Data Management System, because that's what I've been doing for the last couple of years. And I wanted to talk about all of it, but that would have needed a few sessions to do. So here are the main things that I think I've learned while doing it, and I think this could be useful to hear to other people as well. Some of them are specific to cloud-native geospatial, but other lessons can be useful more in general for building any kind of complex software. So what have I worked on? This is what is called the RimRep DMS, which is a data management system that needs to work for the Reef 2050 Integrated Monitoring and Reporting Program. This is a program about managing the Great Barrier Reef, and the part of the program that we're building is the data part, where we set up a data management system where we collect data sets from several different organizations. We go to each of them, get their data, convert them all to cloud-native formats, and make them all available on a single platform. So this would make it much easier for researchers and policymakers to get the data they need to do their work without having to contact lots of different public and private organizations to actually get the data they need. So we have a few components of the system. I'm not going to go into great details about them, but we have a metadata API based on STAC, the Spatial Temporal Asset Catalog. If you don't know what it is, I'm sure you'll hear lots about it during this conference. We have a data API that's based on PyGAPI, which is an open source implementation of the OGC standards. We're publishing features and coverages for tabular and raster datasets. But the main thing I'm going to focus on is our cloud-native data types. We are getting data in several different formats and converting them all to these two formats. One is GeoParquet and one is Zarr. All the data that can be classified as tabular, that can be represented as a table, is going to become a GeoParquet or a Parquet file if the data is missing geospatial information. And this, for example, we're getting CSV file, GeoJSON file, shape files, Excel files, in some cases some particular NetCDF files. The other kind of data we have a lot of is raster data. And this is very often three-dimensional data of the ocean. This could come from most often numerical models of the ocean, but sometimes we also have observation data from satellites or buoys or other sensors deployed. And most often the raster data we're getting comes as NetCDF files or GeoTIFFs, and we convert them all to Zarr. Now, first lesson I've had to learn is how to organize the code for building such a big project. There are two conflicting requirements. One is we want to be able to develop our system fairly quickly, and the other one is we want to have our code be maintainable. And that means, on one hand, we want to be able to just throw down some code and have it deployed as soon as possible. On the other hand, we want to have carefully organized code, well-tested, versioned, and all of that. So depending on our needs, we have settled on three different stages of our code. Especially the main part of code I'm talking about is the one that gets the data from different places, converts it to our formats, and publishes it. So the first thing we do is just write a Python script, upload it to our workflow manager. It's Argo Workflows, by the way, but that's not important for the concept right now, and just run the script. It could be, if the code is simple enough, we could write 10, 15 lines of Python code that loads the data, converts it to Parquet, saves it somewhere. All these can be done very quickly, very easily. I can write a new workflow in 10 minutes, deploy it, and have it running. Now, if we realize that this code we have written can be useful more in general for the future, we could reuse it, we could apply it to other data sets. What we do is package this code as a reusable template. We're still going to have this same 10, 15 lines of Python in a script somewhere, but we are placing this script in a repository where we can access it and we can reference it from future codes ingesting new data. So next time we have to ingest another data set that's structured in the same way, we don't even have to write those 10 lines. We just reference the script that we wrote last time. Next step. Once we decide that some template is actually a core part of our pipeline, we are going to use it several times. We might want to add functionality to it. We want it to be, we want to be able to maintain it properly and version it and all of that. We use the code, we put the code in a separate repository. We actually expand it, we make it into a proper command line tool, we add tests to that, and we package it as a Docker container. Then this Docker container, again, will be able to be used directly in our workflows just by referring to it. We didn't start with this idea, but while working on the project, this came out organically as a good way to balance the requirements of fast development and maintainable code. So first lesson is learn to organize your code so you can do both. My second lesson learned is on big data. We can manage large data sets. Most of the tools we're using have no limitations on the size of the data. You can just use them. We are running stuff on the cloud. You can always request more memory and more computational power. Nothing is a problem at all, except sometimes the data is very big. And we realized that we had some fairly big data sets. Here's a couple of examples. One of them is a 30 gigabyte CSV file that, if you ask me, it's a terrible idea to have a 30 gigabyte CSV files, but that's what we got, and they gave us this data in this form. They're publishing it in this form. We have to convert it to a Parquet data set. Another example is a collection of netcdf files. In total, it's more than 1 terabyte of data, and we want to convert it all into a single Zarr data set. In theory, both of these things are doable. In theory, we can do them in the same way we would do for smaller data sets, just requires more memory. In practice, we faced a bunch of different issues. We kept running into errors. The normal approach didn't work. What do you do in this case is quite simple in theory. You just take your data, split it into chunks, work on each independently, and then figure out a way to merge them in the end. And this is the approach that we've taken every single time something became too large to manage. Divide and conquer, it's a very old strategy. It still works today. So remember that when you have to deal with something too large, that's what you do. Now, getting into more specific stuff, the Parquet format, maybe some of you is not very familiar with it, but what Parquet is a tabular format that's column-oriented. So if you imagine a normal table, you have the first row, second row, third row. Here we're storing first the first column for all the rows, then the second column, and so on. This has some advantages. For example, all the data in a single column will be similar usually, so it can be compressed very efficiently. Some data sets will have lots of columns, but when you analyze them, you're only interested in a handful of them, so it's easier to read some selected columns from a file. And it has, now I'm oversimplifying, but Parquet has a lot of little tricks to make the data smaller in size and faster to access, to query, to filter, to analyze. One important part of Parquet is the concept of row groups. Now I said that you have a full column and then a full other column. That's not entirely true. The first thing Parquet does is split your table into groups of rows. This could be a few thousand rows for each group, and then store each group one after the next. So then internally to each group, you will still have the first column, second column, third column, but you have this organization of the data that together with that, Parquet is also storing statistics for each row group, so it's able to know if some queries you're running should look into a specific row group or not, so discarding entire rows even before looking at them. So what we realized is that this is very important for efficiency when you're working with large amounts of data. Simply by changing the size of the row groups, we were able to get query speeds up to 5 times faster. And that's because if you have the standard way that you might, if you don't set any specific parameter, what you get in the base behavior converting, for example, a CSV to Parquet is just usually one very large row group or a few very large row groups. But if you reduce the size of your groups, of the groups of rows, you are able, when you query, to filter them more efficiently. You can discard 70% of your row groups before looking at any of the actual data, and so all the queries are way faster. In addition to that, if you sort your data properly, this gets even better because let's say, for example, we sort the data temporally, so we have all of it from the beginning to the end, and then we split it into row groups. What happens is each row group will contain maybe 1 year of data or 1 month of data, depending on how your data set is organized. When you query your data, you want to get the data from a specific day, it's very easy. You throw away all the row groups but one, because you know that the date won't be in range for those, and you just need to look at 1,000 rows or so. These made huge differences for some particular kind of queries. The trick is you need to know what kind of queries you're expecting to be run on your data set. You can't do this to make it faster in the general case, but if you have an idea of what your users will want to do, this can make a huge difference. Another optimization that we did was based on the dictionary encoding of Parquet. Now maybe I will not go into too many details of this, but basically all the data inside a Parquet file is compressed. One technique for compressing the data that's used is a dictionary compression. And you don't need to care about it, but if you do care about it, you might find out that it makes a big difference. We had one particular case where one data set ended up being about 2 gigabytes in size once converted to Parquet. We realized that the way we were managing row groups and dictionaries resulted in very large dictionaries for each row group. We changed some parameters, forced a limit to the size of the dictionary, so once you get over a certain size, it's better to leave the data uncompressed. And we ended up getting the data to 8 megabytes, which is crazy. Now, switching to Zarr, our other cloud-optimized format. Zarr is data format that's very similar to netcdf, for those of you who know what netcdf is. But the main idea is you have multidimensional data often in our case, we have latitude, longitude, depth, and time, so 4 dimensions in a data set. You split this data into cubes, or hypercubes if it's more than 3 dimensions, and each of these cubes is saved in a separate file. Then there is an index of these files, so when you're trying to look up data for a particular region in time or space, you just check the index, you know exactly which of these small files you need to load, and you don't have to look at the whole data set again. One important concept again here is the chunking. So in Zarr, you can organize these cubes however you want. They can have the shape you define them to have. And one very common case is we get a collection of netcdf files. These files are being published by some organization collecting data. They publish a new file every day. And then what you do is you take maybe years of these files, put them all together in a single Zarr data set. But if you just do it the naive way, what you get is one chunk for each file. So every day will be stored in a separate chunk, but you don't have any subdivision on the space. If you put some more work into it, you can define a chunking strategy, and you can decide maybe we don't need to keep each day separate. Maybe we can have each month be a chunk, and maybe we can also chunk the space. So we define a grid on our data, and each square of this grid will create a new chunk for our Zarr data sets. This means when you want to extract a time series for a particular location, you will only need to look at the chunks corresponding to that location. While if you want to draw a map for a specific point in time, you will need to look at only the chunks corresponding to that part of time. This, again, can make a big difference when changing from one chunk per day to also chunking in the spatial dimension. In one case, we managed to change the time to plot a time series from minutes to seconds. Again, more details about stuff you can do in Zarr and stuff you need to care about is that rechunking can be hard, especially if you want to update your data over time. So it's easy to take one data set and set a chunking strategy and convert it to Zarr. But then if the next day a new piece of data comes in and you want to add it to this, you need to be careful because, for example, as I said, we decided maybe to chunk each month in a separate chunk. A new day comes in, you need to add it to the last chunk. You don't create a new one. So you need to reprocess the last file and add the new day in. There will be a lot to say about this, but the main idea is just be careful. Another lessons that we learned is that you can update your data set whenever you want, but maybe you should do it only when you need to. We have automated workflows updating our data. Initially, we were running them every day. For every data set, we re-ingest it, we update it. We became a bit smarter about that. We set up some checks so that we know if the data has been modified or not, if there's new data to ingest. If not, we just keep it. Another important lesson is interoperability. This is easy to forget. Not everybody uses the same tools you're using. We want to publish fair data. We are following open standards. It's still worth checking that what you're doing works with what other people use. And some things we found out, for example, is that several of our customers, of our clients are using R, and they couldn't read Zarr datasets from S3. And also the metadata from Parquet files couldn't be read easily from R. So to solve these, we focused on the data API that our clients can use to connect to a server that processes the data for them. and we stored metadata separately and not internally in the Parquet datasets. I think I'm running out of time here because Dawn is looking very angry at me. So I will skip a few lessons that could be important, but you'll figure them out yourselves. When things go wrong, when things go more wrong, and when things go very wrong, this will happen to all of you. I don't need to teach you about that. Just one interesting story we had. No more interesting stories. We're done. Thank you for listening, and sorry for being too talky.
Okay, anybody got any questions? Yeah.
Just on one of the last slides there, you had some references to R and metadata standards for Parquet. A few years ago, it was probably at one of these conferences, like maybe 2019, there was a lot of buzz around R, and since then, the slant's been a lot more towards Python. What's your opinion? Is one better performing than the other, or is one better to use?
Well, my personal opinion is that Python is better, because that's what I work with. No, the reason we focused on R is because we developed this system for mostly oceanographers to use. Physical oceanographers tend to use more Python and MATLAB, but biologists tend to use a lot of R. I'm not an expert in R. I've used it very little. I've been told that it's got some great libraries for statistics. I've also heard you can do the same things in Python, and Python is generally easier to use to do everything else. But we just need to acknowledge that there are some fields where there has been a lot of code developed, and there are lots of tools being developed by researchers, scientists, or other people in a particular language. So it's hard to decide to just let's switch languages and lose all of that code. So if you need to start a new project and you don't have any legacy to follow, I would say go with Python. But be aware that in some cases it's not really an easy decision to do, and lots of people will want to use R, for example, and you don't want to just tell them, bad luck, our program doesn't work for your purposes.
I'm sorry, in the interest of time, can I ask you find Leo near the registration desk later? I'm sure he'd be very happy to talk about the bits of his presentation that he couldn't cover. I have to move on with this session, so I'd like you to join me in thanking Leo for his presentation.